Well, here we are. We're approaching the end of the semester here in Physics 111, Dr. Weaver's class, and we're on Project 3. Our team members for this project are going to be Robert, Ben, and Corey. And I'll bet you're never going to guess what our project is about. Okay, I could be wrong. You probably guessed it the second you heard the sound of the crowd, and for sure guessed it when you saw the guys chasing a little black and white ball. Well, that's it. Hopefully, unlike other programs you might have seen about soccer, this one is a little unique. Unique in the fact that it's about a very specific part of the game. Specific because, well, let's just put it this way. We're only going to be talking about the ball. Yes, just the soccer ball. Okay, there might be, we might talk about the forces that affect the ball, but for the most part, we're just going to be talking about the ball. And now for a little primer into exactly what we're going to be talking about. Take a look at this CBS News video that talks about Beckham and how he bends the ball.
On the Galaxy's home field, he gave us a rare look at how he does it. Can you sort of go through the setup to the kick?
It's literally finding the right place and keeping it there. This is where I start. It looks like I'm kicking the ball over there. But what I'm doing is I'm able to come to this angle, come round the ball and whip it.
Are you looking at the net at all?
I literally stand here, take one look at the goalkeeper, and then just concentrate on the ball, because I know that if you put it in the exact spot where you want it, there's no way the goalkeeper's going to get there. And then coming round, and it's that side of the ball, like that. You want to go in goal?
Yeah, I'll go and go.
Then you can experience not being able to see.
All right, that'd be good.
Trying to stop his shots is as bruising on the ego as it is on the body.
Wow.
So let's jump right into this and take a look at a few simulations of exactly what's happening to the soccer ball. We're going to go ahead and show you several point of views. The first one here being as if we were standing directly behind the kicker. In this case, the kicker applies no rotational force to the ball, and thus it goes in a linear motion. In this next scenario, the kick is applied with a substantial amount of rotational motion, which allows it to curve, in this case, to the left. Here we see an overhead view of that same shot with no rotational force. And once again, an overhead view where the force is applied in such a way to give rotation to the ball and allow it to curve. And then finally, we're able to see a side view here where we can see the ball is kicked and it travels towards the net, and it actually goes up and then back down as it does so. So where do we start? What data do we need, and where do we get it? In our case, we use video analysis to begin our understanding of what is happening, and we started with the first phase of the analysis, which is the kick. The video analysis software we used is called Logger Pro and is available from Vernier Software and Technology free of charge at www.vernier.com. We started by using the analysis software to retrieve two things. First, how fast the ball was kicked, and second, how long it took the kicker to do so. We knew that if we were able to get the two numbers, we would be able to calculate the force that was exerted on the ball based on the concept of momentum. One way to determine the force applied to an object is by multiplying the mass of the object by the acceleration of that object. This would be the simplest way to find the force that was applied to the ball by the kicker. Another way to calculate for this is by finding the change in velocity and dividing that number by the time it took to bring about that change. In our case, we were able to determine the change in velocity and the time it took to make that change by using logger pro. One way to determine the force applied to an object is by multiplying the mass of an object by the acceleration of that object. Another way to calculate for this is by finding the change in velocity and dividing that number by the time it took to bring about that change. Okay, now, well, the force, or how hard we kick the ball, is great and all, but what does that have to do with the ball bending? As we'll see here in the next video clip, it has everything to do with how the ball bends, because it's where the force is applied that allows it to do so.
It's a technique that allows players to shoot around walls, or simply outwit goalkeepers by causing the ball to change direction after it has been struck. So while mastering this technique took me a few years, you're going to learn and understand this technique in just a few minutes. So if you'll notice, when I kick the ball dead center, it goes just as you'd expect, straight. But when I kick it a little bit off center, it curves. So now I'm ready to bend the ball. But how do I determine which way the ball will go? It's actually kind of funny. When I kick the ball on the right-hand side, the ball curves left. But when I kick the ball on the left-hand side, the ball curves right. But what's the science behind these curves? It's actually the same principles that allow airplanes to fly and race cars to stick to the ground. The forces of lift and drag. Relative to the center of the ball, the air on the side of the ball with the red arrow travels faster than that of the blue side, simply because it is parallel to the flow of air against the ball. This creates a high pressure area on the blue side of the ball, which actually pushes the ball toward the low pressure area on the red side of the ball. This tangential suction, in aerodynamics called a lift force, creates the curved ball path that would not be exhibited by a non-spinning ball. So now that you know how to bend the ball, try to practice and master the skill. Soon you'll be able to impress your friends and coach, and maybe one day you'll actually bend it like Beckham.
Here we have the force diagrams for the ball in the two phases we've been looking at. The first phase, where it's moving away, speeding up, we have the top view, and the side view with the accompanying forces. The second phase is the constant speed, moving away. Once again, we have the top view and the side view. Seeing how some might view these diagrams as somewhat boring, we'll go ahead and throw in the motion diagram as well. Enjoy. Now that we've calculated the force that was applied to the ball and how applying that force to a specific location on the ball can affect its direction, let's take a look at the data we recorded and see how we were able to document this bending effect known as the Magnus effect.
Clings to me like cellophane, fake plastic submarine, slowly driving me insane, but now that's over.
In the data we analyzed, the ball traveled approximately 2.8 meters to the right, and then, due to the Magnus effect, traveled back 1.4 meters. This resulted in a bending of 1.4 meters.
On every word.